So today I'm going to talk about a work that I've been working on collaboration with Richard, who just gave the present talk. And it is a way to simulate a disordered potential using the Bose-Polaron Hamiltonian that is encountered in cold atoms. So maybe as a brief introduction, because maybe not everyone here is familiar with disordered physics, I'm going to recall very briefly why is it important in quantum physics and what is the mechanism. So we've learned this morning that if you want to explain electronic transport in metals, it is crucial to use disorder. It is also useful to study the transport of waves through matter. So for instance, if you shine light at some disordered material, for instance a colloid, then you will have some interesting phenomenon, coherent backscattering or speckle patterns. And of course, the most famous effect of disorder is the so-called condensed-matter. So if I might try to give an example or, an explanation in a few sentences of what does this happen. So consider here this little sketch. I consider a medium made of scatters, which are positioned randomly, and I try to propagate a particle from site R prime to site R. I will try to compute the density at time t, which would be roughly given by the probability for the particle to go from one position to the other. If I write this as some kind of semi-classical approximation, I would say, okay, to go from one point to another, the particle will go from scatter to scatters, experiencing scattering events until it arrives. Because the particle has to be treated in this quantum mechanical formalism, I would say that the intensity is expressed as the modulus square of the sum of all possible paths of some quantum amplitude. So I can decompose this expression as the sum of two terms. One of them is simply the sum of the intensities, which would correspond to some classical diffusion, and the other would be some interference term between different quantum paths. So when you perform disorder average over all possible configurations of the scatters, in general, this term vanishes. But this is not always the case. And in the case where it doesn't vanish, it can lead to corrections, which could either hinder the diffusion of the particle or even completely kill it, that is, localize the particle. In 1 and 2 dimensions, in presence of disorder, quantum systems are always localized, while in 3 dimensions, there is a transition with the strength of the disorder between a regime where states are localized and a regime where states are not and are delocalized, separated by a mobility edge. So the theory of Anderson localization has been initially developed to understand transport in some solid-state physics devices, spin transport in doped semiconductors. But the problem with solid-state physics, which is also the reason why it is rich, is that there is a lot of phenomena at interplay. And for instance, one might say, what are you seeing? Is it Anderson localization, or is it, for instance, some Mott insulating behavior? This is why, afterwards, experiments have been more focused on studying Anderson localization with waves. As I've just explained, it is at heart a wave phenomenon. So here I'm studying experiments with microwaves or light waves. So for instance, what they have realized is some photonic lattice in this transverse XY direction, and they shine light at it. So they can add a disorder in this transverse direction, and depending on the strength of the disorder, either this light waves propagates transversely or it does not. More recently, in the Alain Aspect group close to Paris, they have made an experiment for the expansion of a Bose shell condensate. So they have studied Anderson localization with a matter wave. They prepared the system in this Bose shell condensate, and they observe its expansion through some speckle potential, which is made with light. Depending on the strength of the speckle potential, they observe either a spread of the wave packet or a localization. So that's it for this introduction, and now I would like to present, to go to the bulk of this presentation, which is a mapping between a very simple or time model for disorder and an Hamiltonian, which can be realized in quantum optics. So the model that for the disorder that I'm presenting is the so-called Edwards model. It describes the motion of an electron through a metal with some impurities. So the Hamiltonian simply consists of the kinetic energy for the Hamiltonian but they also include, for the electron, but they also include n scatters, which is positioned at site R, and which interact with the impurity through some potential V of R. And of course, the potential is given by the sum of the potential of every scatters. Where does the randomness come from in the system? From the possible positions of the scatters. So we choose them randomly, and let's say we're in a box. We choose them with some uniform probability. And if you want to compute some disorder averages for your problem, then you're going to fix a configuration of disorder, so sample your points, compute the evolution of the wave function for the electron, and take the average. So this is how you determine the disordered average quantities of the system. Now let's move on to the Bose-Polaron model that I'm investigating. So I think we've heard quite a lot about this over the past few days. I'm just going to fix the notations here. I'm considering a single impurity, so of course there is no interactions. And because it's a single impurity, I will be describing it more with its wave function. I couple this to a Bosonian condensate, so I just take a bosonic bath with no interactions either. And of course, at the initial time, I prepare the bosons to some Bosonian condensate. So both of the species are without interactions, but of course there is an interspecies interaction, which is simply given by a density potential V of R. I must stress that the problem of the Bose-Polaron, as has been, I think, recalled by Jacques in his initial presentation, has been studied experimentally. So here I cite maybe 3 different mixtures where I think the spectral function of the Polaron has been determined. So in which case can we go from this model to the disordered model? Well, in the case where the bosons have an infinite limit. And maybe to prove the mapping, I'm going to go in 2 steps. The first one, I assume that the bosons, so the bath, are localized at fixed points, at fixed positions, R1 and so on, Rn. Because we assume that the bosons have infinite mass, they are completely motionless. They are immobile, and they will represent the fixed scatters from the disordered model. In practice, this means that if you let the system evolve, then the bosons are in this state at initial time, while they will remain in the same state at time t. On the other hand, the picture is different from the point of view of the impurity. The impurity is these n scatters, which are a fixed position Ri, and will evolve through this effective single particle Hamiltonian, which is nothing but the Edwards Hamiltonian for the given realization of disorder. So now let's move on to the second part of the proof, which is simply to remark that the Bosonian condensate is given by having the n bosons in this zero momentum state, which is, if you Fourier transform, a superposition with equal weights of a position boson 1 at site 1, and so on. So the state, which I prepare at initial time, some wave function times the BC, is written as this superposition. And each of the states in this superposition are going to evolve separately, with the bosons remaining in the same state, and the impurity evolving with this Edwards Hamiltonian for this given realization of disorder. Now, if you measure an observable acting only in the impurity, what will appear is that because of this superposition of states, it will realize the average over disorder. So you compute an observable within the many-body system, and what you get is an average over disorder. So just to sum up what we've obtained, we are looking at this Bose-Polaron model, which is a model, a many-body physics model with interactions, but which is free of disorder. And with this mapping, we have proven that by observing and making this measurement, you can get the disorder average value of the quantities for this single particle Edwards model. So you kind of trade in one difficulty, the many-body aspect, for one other, which is the disorder aspect. Now, let's maybe take one step back and think about the generality of the mapping, and in which case what we've looked at is valid. First of all, we did not make any assumption on the potential. So even if later on we are going to consider contact potentials, this is also true for more generic interaction potential between the impurity and the bosons. Furthermore, it is not important if there are interactions between the bosons in the Bose-Einstein condensate or if there is a trapping potential. The only thing that will change will be the potential to which the bosons, will be the ground state wave function for the Bose-Einstein condensate, and this ground state gives you the probability with which are sampled the scatters in the equivalent Edwards model. So you can probe more complicated models of disorder, and even if you're a bit crazy, change the bosons for fermions and look at this probability distribution, which would be the ground state of a Fermi sea, which would be very complicated and with long-range interactions. Lastly, this mapping remains valid if you start to add in several impurities. So let's say you could consider a Fermi sea of impurities and make a transport experiment, and you would like probe metallic behavior. Or you can add interactions between these impurities and check the interplay of many-body physics, interaction physics, and disordered physics. Of course, this mapping is limited in one big way, and this is that in real life, the mass of the bosons will necessarily be finite. So the hope that we have, which has not been confirmed yet, is that if you look at short times, the bosons will not have been set into motion by the interaction with the impurity, and this approximation will remain valid. And of course, at larger times, through interaction with the impurity, even if they are massive but at finite mass, the bosons will start to be set into motion, and this picture will start to be scrambled. So let's just give maybe, let's say, some hope for observation. We are looking for a mixture with a very large mass ratio, mass imbalance. And an example which has been, maybe the properties of which have been examined in this paper would be lithium-6 impurities in a Bose-Einstein condensate of cesium, which achieve a mass ratio which is of more than 20, which is almost infinity, let's say. So if you subject this mixture to a magnetic field, there is a Feshbach resonance close to this magnetic field, at which you can tune the interaction between lithium and cesium, while the interaction within the cesium atoms remain not too big. The idea or the ideal goal that one would like to observe in this kind of system would be, for instance, three-dimensional Selflocalization. So the rule of thumb, I picked this from Erika Kerman and Gilles Montalbot's books, for this transition to appear in a metallic system would be to compare the Fermi wavelength and the elastic mean free path, which is a measure of the strength of disorder, which would be a typical distance between scatters. So the transition is said to occur when this number is of order of 1. So in the Edwards model, you can deduce this elastic mean free path from the properties of the scattering potential, and it is given by this expression. It depends on the scattering length between the two species. So kind of the idea that we have is that maybe you can have this elastic mean free path reasonably big, and at the same time, the momentum of the impurities not too large. That way you would be in a regime where free body losses would be not too important, while you would still be able to see the Anderson transition. What we've been doing on top of this is some kind of simple numerics. So disorder, at least from a theory point of view, is a subject which has been very widely explored over the past 50 years with a lot of very, very complicated and very involved methods, diagrammatics, and so on. What we wanted is to kind of look at something opposite, a very quick and dirty method that you can run on your laptop while you're sitting here in the audience, and kind of see, can we recover even simple physics of disorder? So the method we've settled for is the time-dependent variational method. So it kind of consists in 2 steps. The first one is to use the celebrated Lilopines transform, which is simply the idea is to go to the reference frame of the impurity via this unitary transform. So in the initial problem for the Bose Polaron, the impurity and the bosons have no interactions, but of course there are interactions between these 2 species. By doing so, you go to the reference frame of the impurity, then its momentum is conserved. So if you prepare the system in a plane wave for the impurity and a Bose-Einstein condensate, after this transform, the impurity will remain in the same plane wave, which is simple, while you will have picked up interactions for the bosonic part. So after this mapping, what you have to do is to solve simply a problem for bosons, but with interactions. And this Hamiltonian, for those of you who were here this morning, should remind you of what Robert Selling spoke about this morning. On top of this, to study this Hamiltonian, we approximate the Bose-Einstein condensate wave function by this coherent state, which will be time-dependent, which is also an approximation which was mentioned this morning. And you find the coefficient of this coherent state by finding those that best approximate the Schrödinger equation. And let's look at just a simple but still very, very interesting result that we find with this, the spread of our wave packet. So let's say we make the following protocol. We prepare the bosons in that Bose-Einstein condensate, and we prepare the wave function, the impurity wave function, in some wave packet at time t equals 0. And then we tune in the interactions and we see what is going on. So first, if one has no interactions, you all know what is going to happen from a quantum mechanics 101 course. The wave packet is going to spread with the width of the wave packet, which is going to increase linearly. On the other hand, if one has localization, you expect the wave function to be exponentially suppressed, and this is what we observe. So that's what I show in this plot. This is the density versus the position for different times, and in this logarithmic scale. So at the initial time, we prepare the system in this Gaussian wave packet. You see this beautiful parabola, and you let the system time evolve. The dashed black curve tells you, for reference, what happens for the free system. The wave packet just spreads. While, on the other hand, in the case where we tune in the interactions and we have a finite disorder in the equivalent model, we have an exponential localization with this linear plot in this logarithmic scale. So you can also measure the width of the wave packet, which is just given by this observable. And of course, in the case of the free wave packet, it increases linearly, while on the other case, where the wave function is localized, it saturates. So these are still preliminary results. Even if we have started to investigate transport, and for instance, if we look at what happens when we subject the system to an external force, we see subdiffusive behavior. If we look at the wave packet with some initial momentum, we see it move over some length and then stop. So even if we have this encouraging first result, this is still not complete. In particular, maybe I'm starting with the prospect side part of the slide. We want to learn more about what happens with transport, and we want to learn more about what happens in finite mass behavior to kind of go to the regime of the experiment and see, can we still see something happening? Maybe the outlook and the conclusion, what I want you to remember from this presentation, is that we have this nice and exciting mapping, which would have allow to maybe explore disordered physics with a new light, maybe both on some experimental side with a new setup, but also for maybe theory or numerics. Maybe solving the many-body problem would be more fun than doing disorder average or replicas or whatever horrors you can devise. And lastly, we made this very quick and dirty calculation with the variational method and still got some powerful and fun results. So I thank again Richard, with whom I've been doing this work. So I think you can still remember his face, but still. And I thank the audience for attending this presentation, even though it's the last one of the day. And I'm open for questions. Yes?
It is known that in localization problem, many quantities are non-self-averaging. That is, you have a unit
Yes.
just of the average of transition. So I do not catch your point when you say that performing a measure, I did the disorder average.
Yes.
I would understand that once you perform a measure on a given organization of the scatters, then you get the typical bubble rather than the average bubble.
So like the point is that here you get everything. So some quantities would not be self-averaging, which is the difficulty of disorder. So like what I'm saying is that with this single measurement, you have all possible values of disorder.
You have a single realization of disorder.
No, all of them, because of this quantum superposition. So like here, the average over disorder is done by this integral because I took the uniform distribution.
So if you sum up, if you have a process which has, for example, log normal distribution, and you have only one sample, and you sum over the sample, then you don't get the expectation part.
Yeah. So this also depends on what you put inside the observable. So, of course, yeah, so if your point is that if you measure something which is self-averaging, you don't need this formalism, but then this is also valid for something which would not be self-averaging. Yes?
One of the big goals in the field is to observe the impurity interactions mediated by the medium. So
Yes.
is this another way of looking at mediated interactions?
So like, I'm not sure if I completely see the question because I discussed this the other day and someone gave me this very naive remark. If the bosons are not affected by the motion of the scatters, you don't really have a polaron. You just have an impurity moving through this potential because there is no feedback. So in this limit of large mass, you would expect the feedback to be small. Then maybe if you're saying, maybe let's see what is the difference between small and zero, yes, I agree with you.
Yeah, maybe in this case it's particularly not mediated because the medium is so heavy.
Yeah.
So, in what sense is this localization different from strong coupling Polarons?
So there is no lattice here to... Yeah. So I would say that strict... Yeah. So I would say that when I speak about localization here, I'm thinking first at the equivalent disorder model where there is no interactions. So this is not something which there is a mapping. So of course in the Bose-Polaron model you have interactions, but the equivalent model you have none. So, maybe I don't want to make any claim here, but this would maybe mean that there would be an equivalence between self-localization for the Polaron and some localization in the disordered model.
But there is no self-localization of Polarons.
There is no what?
No